Welcome, everyone. My name is Ivey Chiu. I'm a senior data scientist at Telus and AI R&D lead. I'm a presenter today along with my colleagues Vince and Dominic, and we're here to discuss an application of model-based reinforcement learning to reducing energy consumption in Telus data centers, which was a Telus Vector collaboration on the development of what we term the energy optimization system. So this is the outline. So first I'll go through the introduction along with my colleague Dominic. Then I'm going to talk about the industry implementation, and I'll pass it off to Vince to talk about the AI implementation and then to discuss the results and innovations. And then I'll wrap up with the next steps. So in this talk, we discussed the motivations behind a Telus Vector Institute collaboration to apply model-based reinforcement learning, or MBRL, to the reduction of cooling energy consumption in Telus data centers. Costs to operate data centers, including the heating, ventilation, and air conditioning, or HVAC component, can be large. In fact, data centers accounted for 1.8% of power consumption in the US in 2014. Given a set point in HVAC, it is a challenge to optimize the control of cooling while also considering various other inputs such as weather. So here we recognize the opportunity for an application of MBRL, and we developed an algorithm to build a simulation that showed a potential energy savings between 2.5% to 15%. Furthermore, we developed an algorithm innovation that we termed hyperspace neighbor penetration to deal with slowly moving variables such as temperature. And also in this talk, we discuss the Telus Vector journey to deliver this AI solution with real-world applications. So just to introduce Telus, Telus is a dynamic, world-leading communications and information technologies company. We're committed to using our technology for good and to help make our world a better place, such as in making healthcare more accessible, creating a safer food supply chain, and connecting Canadians when it matters. Dominic?
Thank you, Ivey. So sustainability is a cornerstone of our future-friendly promise that we've made to the customers. So in 2010, we settled on the journey, and as a result of the spirited teamwork that everybody put together, we've basically reduced our overall energy consumption 17% below the 2010 numbers in 2020. So we've been looking at technological solutions to basically reduce our impact on the overall world. And essentially, we're now setting goals for 2030, where we will reduce our energy intensity by 50% by 2030. Well, thank you, Ivey.
Thank you. Now I'll just introduce the Vector Institute. The Vector Institute's mission is to drive excellence and leadership in Canada's knowledge creation and use of artificial intelligence to foster economic growth and improve the lives of Canadians. Currently, they have over 500 researchers and over 45 industry sponsors, of which Telus is one of them. And within the industry program, they have 900 plus industry program participants. So the Telus Vector collaboration is under the umbrella of their AI for Good initiative, which is operated by Vector's industry innovation team. So this project is actually posted on their blog, and if you have a chance, please head over to the Vector blog and read more about this project. But we'll cover everything here as well. So now I'm going to talk about the industry implementation, discuss some of the processes, challenges that we encountered in this implementation. So first of all, the key internal partner, so the key internal Telus partner is Mission Critical Environments, so MCE, which is headed by Dominic. So the MCE team provides the long-term strategy, end-to-end leadership, and operational support for power and cooling of our critical environments, including data centers, central offices, and other key facilities throughout Canada. So Dominic's team was key in helping us to understand the technical aspects of HVAC, as well as helping us being able to actually connect to a pilot site and finding that pilot site in the first place. Other key technical and operational stakeholders that we worked with since pretty well the beginning of the project included building management, so the team that actually primes and owns the facilities. Network operations, so that's the team that actually owns the network equipment that resides inside the facilities. And we also worked extensively with the HVAC vendor, first to understand the behavior of the HVAC equipment that was in the pilot site, as well as working with the HVAC vendor on various software changes that were required in order for us to actually implement the AI algorithm. Additionally, we developed and piloted this program with Telus's commitment to a responsible AI at the top of our minds from the very beginning. So this includes operating with trust and transparency, which is what we did by involving our stakeholders from the very beginning. And also what this does is that this helps to create opportunities to proactively impact social good with the use of technology and AI. So one of the takeaways that I want to point out here is that implementing AI to control disparate physical systems involves many stakeholders, and it involves working with them in a cross-functional fashion from the very beginning. So now I'm going to pass this on to Vince, my colleague, who will talk about the AI implementation itself. So Vince?
Thank you, Ivey. Hello, my name is Vincent Jia. I am a lead data scientist in Telus. I will talk about the AI implementation and later the result and innovations. Can you go to the next, please?
Sure.
Thank you. The goal of the AI project is to regulate the indoor temperature and ensure it is at or below the set point, which is 23 degrees. And meanwhile, the AI needs to minimize the cooling energy consumption. By the way, our AI can also regulate the heater so it can run actually all year round. In addition, the AI needs to satisfy other requirements, such as allowing the compressor to rest enough in between cycles. The means under the AI's control is to make a choice from 3 options every minute. Option 1 is to run the compressor, which is expensive but very effective in cooling. Option 2 is to run the free cooling, which is very cheap but very less effective in cooling. Option 3 is to idle. So the task is like a chess game. Players make a move in each step, and a good player knows to sacrifice the immediate steps to gain more in the long term. We will see how it happens with the AI later.
Next slide.
Yeah, next slide, please. Yeah. Thank you. The project uses reinforcement learning, which is very similar to the learning of human being exploring the world. The robot agent studies the actions and the consequences and eventually find out a path to maximize the long-term reward. Reinforcement learning is the future of machine learning. It's goal-oriented and it's innovative. I will introduce the innovations made by the AI later. Reinforcement learning is aimed at achieving long-term effect, and it doesn't require a large data set. In our AI implementation, we have built 2 things. First, we built a virtual simulation environment, which allowed for testing safely. And more importantly, it expedited the learning. The agent could acquire hours of experiences in real world in just seconds in the simulation. Second, we built a robot agent to learn. We used model-based reinforcement learning, and we made an algorithm innovation, which we called hyperspace neighbor penetration. I will talk a bit more about it later. Go to the next slide.
Yep.
Thank you. Now I will talk about the result and innovations. This slide illustrates the innovations made by the AI. There are 2 charts here. The one on top is the true record of a typical day. It covered 24 hours from midnight to midnight. The green line is the indoor temperature. It was regulated by a conventional HVAC unit. HVAC stands for heating, ventilation, and air conditioning. The yellow line is the outdoor temperature. It is a big influencer of the indoor temperature. The chart underneath is the AI simulation of the same day. It started from the same condition, and the outdoor weather in that day was also the same. It is like we first let a human play a game, and then let the AI play the same game again for comparison. The AI made 5 innovations. Number one, we can see from the bottom chart that right from the beginning at midnight, the agent let the indoor temperature rise up and to the set point of 23 degrees over a period of about an hour and a half and stabilize it from there. This is in clear contrast to the conventional control on the top chart, where right from the beginning, the conventional control kept running the free cooling and pulled the temperature all the way down to a low level of 19 degrees and maintain it there. The benefit of this AI decision is clear. Maintaining a higher temperature is more efficient. The number 2 innovation by the AI is more astonishing. As we can see from the bottom chart, starting from around 6 a.m., the AI agent ran all out the free cooling, pulling the temperature down as much as possible before it rose up. So on the chart, it made an interesting, and I would say a beautiful curve. Why did the AI give up the most efficient way of maintaining the temperature at the set point and instead ran all out the free cooling? Although free cooling was very cheap, it still cost it, right? This was because the AI considered the weather forecast. It noted that the outdoor will be very hot in the afternoon, so it cooled down the room early to delay the using of expensive compressor later. This was the hallmark of reinforcement learning. The agent sacrificed a little to avoid bigger costs later. Number 3, every time running the compressor, the agent pulled down the temperature by a flexible amount. Number 4, the agent more actively leveraged the free cooling. Number 5, the agent reduced the temperature by a smaller amount when running the compressor. All the innovations made by AI can save the energy by 2 to 15%, and maybe even more, as our measures are a bit conservative. Go to the next slide.
Okay.
Thank you. So here, I would like to introduce our algorithm innovation that we call hyperspace neighbor penetration. First, I point out the problem with the classical dynamic programming and its variants, such as tile coding. On one hand, dynamic programming is suitable for our project because it involves no randomness in learning. It has very few hyperparameters, and it is faster than other algorithms that we have tested, mainly because it doesn't require many trials to converge. On the other hand, we need to handle the temperature, which is a slowly changing variable, but the classical way cannot handle. The reason is that the classical way cannot capture the tiny changes in each transition step because it is very computationally expensive or impossible to establish an extremely granular grid system to discretize the continuous state space. As such, we developed the HNP algorithm. HNP captures in each transition step the state's partial penetration into its neighbor's hypertiles in the gridded hyperspace. So it doesn't require the transition to be intertile in order for the change to be captured. Therefore, HNP allows for a very coarse grid system, which makes the computation feasible. As a result, HNP is orders of magnitude more efficient than classical algorithm in handling slowly changing variables in reinforcement learning. And it is the backbone of the project. We have submitted a paper on HNP to another venue. Thanks. I will give it back to Ivey.
Okay, great. Thanks, Vincent. So now I'm just going to talk about the next steps. So currently, we're running tests to collect more data so that we can actually do some further investigations in energy savings in the actual application at the pilot site. So we're running that right now as the weather is getting warmer and cooling is required. Additionally, we're also exploring ways to scale up the use of the energy optimization system within the Telus networks. So we're doing this in several different ways. One, we're looking to implement it in more of our small rooms across the network. We're also looking at being able to scale this to larger, more complex rooms. And we're also looking at open sourcing this to the wider AI and HVAC community so that the rest of Canada and the rest of the world can actually derive benefit from the work that we've been doing with our research partners at the Vector Institute. So with that, I'm going to conclude. I'm going to say thank you, and I look forward to answering any extra questions that you may have on Tuesday. Thank you.